Okay, so welcome to our session for today. We have here a frame subjected to a loading. Again, it is involving a diagonal member here, AB. So this is a frame wherein, again, we take it by section or by member. Okay, so the first step is to determine the reactions first of the roller and the pin support here. So we are going to assume vertical and horizontal reaction at E and a vertical reaction at C. And then as usual, we are going to take moments at both supports to solve for the reaction. So looking at the figure, we need to first resolve this distributed load vertically into its resultant. So this is 40 times 3 equivalent to 120. Then we're going to take moments at E. So we have a clockwise rotation times the distance, which is half of 3. And then for 80, that is a clockwise moment times its moment arm equivalent to 6. Less 8 RC. And that will be equal to 0. So RC is equal to 82.5 kilonewton. So for the other reaction, we have summation moments at C. So counterclockwise 80 times 2 less another counterclockwise 120 times 1.5 less RAX times 3 plus 8 RAY, and that would be equal to 0. So we come up with an equation having two unknowns, RAX and RAY. Of course, if you will look at the figure, we are pretty sure that RAX is simply the horizontal force here by summation forces X is equal to 0. So by equilibrium of our horizontal, we can just say that RAX is equal to 120. And then we go back to this equation. We place the value of RAX and then solve for RAY. So this must be negative 2.5. So if we are going to check the equation first, that is a positive rotation. Okay, so if we check this by summation forces vertical, we have upwards reaction RY. Of course, we carry the sign, plus 82.5 less this downward 80, and that will be equal to 0. So we are quite sure that our reactions are correct. However, we have yielded here a negative 2.5 reaction, meaning we have assumed it on the other direction. Okay, so it should be going downwards. RAY should be going downwards. Okay, as for the next step, of course, we are going to establish now the load diagram, starting with this inclined member AB here. So we're going to place here negative 2.5, and then this is 120, and then this is the upward 82.5, and then we clear the space for our load diagram. So for member AB, we will first work on this 120, so that this 120 here will be distributed parallel and perpendicular to the member. So we need an angle here, say theta, and we note that the slope is in 3, 4, 5 triangle, and then theta is in here because we have here a slope horizontal, slope horizontal. So horizontal line, slope horizontal. See, so this is also theta. So we place the perpendicular and parallel component of 120 with respect to the inclined member AB, so that this 120 here is projected on the other side. We can find it to have, or opposite the angle or the reference angle theta. So we denote that by 120 sine theta, and the other is 120 cosine theta. So using this slope, sine theta is 3/5 and cosine theta is 4/5, which is placed here, and for the cosine theta. So we have here 72 and 96 for this parallel component. So we place next the pointed loads here at A. Perhaps we can now correct the arrow and the leftwards 120 here. So we determine the internal forces at B. So starting with the horizontal, we are pretty sure that we have a 0 value here because 120 rightwards here was already countered by your external reaction here. So 0 is the value of this horizontal reaction. As for the vertical reaction, first, again, it is pretty obvious that 2.5 here is going downwards, so there is no other vertical here. So therefore, this internal force here shall be a 2.5 going upward force. Okay, so with this, we have an initial figure or calculation of this diagonal member AB. So we further polish this calculation by resolving all of your forces parallel and perpendicular to the member. And then, of course, this 120 here will now be distributed to the member AB along its parallel and along its perpendicular component. Okay, so we do that. So this is our member AB. This is 120. We get the component parallel and perpendicular to AB. Of course, we need to involve the angle here. And this is the angle theta here. So that this is 120 cosine of theta. And cosine theta is 4/5. So that this is 96. So for this component, we just have to transfer this. Then extend this one. That is pretty obvious that 120 sine theta. And 120 or sine theta is 3/5. So that the value is 72. Okay, we highlight the components for 120, 72, and 96. So working with the 2.5, so we need also an angle, reference angle for 2.5 for us to determine the components. Okay, we just follow the perpendicular component of 2.5. So follow the direction, and we have here another parallel component of 2.5. So you ask yourself, where is the angle theta here? Let me remind you that theta is referred to the horizontal line. So if we draw a perpendicular line and a vertical line, that is also theta. So we note that this is a perpendicular component of 2.5 in terms of AB. So we apply this rule, perpendicular and vertical. This is perpendicular plus vertical. Therefore, this is our theta. So this 2.5 here, or parallel, is opposite the angle theta if we're trying to project that along the triangle. So here it is. This opposite the reference angle theta. Of course, we use sine theta. And this is the adjacent component. We place the values and the result. We highlight that, so we are done with joint A, coming up with 4 resolved components perpendicular and parallel to AB. So moving on to the member A to B. From A to B, we should have a distributed load caused by this 120 here. So it should be noted that 120 here is coming from or came from a distributed load. So of course, we need also to distribute it along AB. So first, the perpendicular one component of 120 is 72, and 72 shall be divided or equally distributed along AB, and that is 72 all over 5, because our length for AB is 5 meters. So that is placed there. So this is the parallel component that shall be distributed along AB also, the component of 96, and that is to be divided by the length. We have 19.2 for that. Okay, so moving on to the joint B, we have here a 2.5 vertical load. We intend to get the component parallel and perpendicular, and establish your angle. Okay, and of course this is 2.5 sine theta, where sine theta is 3/5. So it will result to 1.5, and for the other component, we'll just have to extend it here. That is actually adjacent to our angle, that is cosine theta. That is 4/5, and it will yield to 2. We highlight the result, so we are now done with B, joint B. So another force or internal force that will be developed on this cut portion, of course, we have here the moment. Okay, so we can just determine this moment using the initial figure here. So solving with the moment at B, we just take moments at B. We have this couple here, less the counterclockwise 120 here, and that 120 is bisecting this 3, so we have a distance of 1.5, less this counterclockwise rotation 2.5 with the distance of, so we have 4 meters, and then we have also here 120 counterclockwise times 3 meters. All of these will be equal to 0. So we have here the value of MB. So let us correct this positive here. So it resulted to negative 170. So meaning MB should be a counterclockwise moment. So anyway, we'll just maintain the direction and then just take note of the sign. So we are done with this diagonal member AB. So we place the couple here, which is 170, and we can actually clean this figure. So this is our AB, the perpendicular distributed load 14.4, so the leftwards 96, and then the leftwards 1.5, the upwards 72, and the downwards 2, the rightwards 1.5, and the upwards 2, and then the couple here 170. So we need also to ensure our analysis by checking the equilibrium equations along the rotated axis, the x prime and y prime. We check the rotated x. We have negative 1.5 minus 96 plus 19.2 times 5, and then the 1.5 here. So is this equal to 0? Okay, so upon calculation, we have that is really equal to 0. So we do the same for the rotated axis at y, an upward 72, a downward 2, a downward 14.4 by 5, and upwards 2. So is this equal to 0? It will yield to 0. So we are quite sure about our solution here, or the correctness of our solution. Okay, so we now proceed to the horizontal member BC. So as we can see here, we have 80 in the mid portion of BC with the 4 meter distance here and 82.5 reaction. So we have here the external forces 80 and 82.5. Also, we reflect 170 and the mother component of 2 and 1.5. So we refer to the mother force of this 2 and 1.5, and it is actually going upwards 2.5. Here it is. So this is just a component, and the mother of that 2 and 1.5 is actually 2.5. So perhaps we can just reflect it here. So if this is going upwards, so this shall be going downwards 2.5. So investigating our member BC along the vertical axis, we have 80 and 2.5 downwards, that is negative 82.5 plus an upward 82.5. So it is pretty obvious that we have a balanced forces along the member BC. So this load diagram is now ready for us to determine the shear and moment diagram. Starting with the shear diagram, we start from A to B. From A, we have 72 upwards minus 2 downwards. We have positive 70, and then we less this 14.4 times 5, we have actually 72, and that 72 is going downwards, so that is negative 72. So 70 minus 72 is negative 2, and it shall be connected by a straight line. So these two here shall close this shear diagram. So a closed shear diagram is an indication of we are doing it right. And then for member BC, we have going downwards 2.5. No load, it will remain to be negative 2.5. And 80 will push it further downwards by 80 units. So this will become 82.5 negative. And then no load remain to be negative 82.5 until it will close to 0 because of this reaction. So here is our moment shear diagram for member BC. So proceeding to the moment diagram, of course we are concerned with this line crossing our 0 shear here. We try to locate this one to compute the area. First, say this is x and this is 5 minus x. And then by similar triangles, we have 70 is to x as to 2 is to 5 minus x. So x now is 4.86 and 5 minus x is equal to 0.14. So we have now the dimension. We are now ready to illustrate the moment diagram. Okay, so we'll just refer to the area and we can move this one. So we wanted to compute the area here on termination of x. Okay, so this is a triangle. We have 1/2 70 times x, which is 4.86. So this is 17.01. We also do the same to the smaller triangle here. We have 1/2 2 times 0.14, and this is actually 0.14. Okay, for our convenience, let us just compute or complete our computation on the rectangles here. Say we have these two rectangles, 2.5 by, okay, so we look on this 2.5 by 2 is simplified, and then 82.5 by 2 is 165. Okay, so let us plot our moment diagram. So from here we do not have any couple. Okay, so it is clear that we do not have any couple, so start with 0, and then this positive area of triangle we have 17.01, And I think we miscalculated our area here. Okay, so we just correct that one. We have actually 170.1. Okay, so we simply place there, and then we less this 0.14 here. So we have a slight difference, 169.96, deducting this 0.14 from 170.1. And then what about this 170? So if we are going to pin this, okay, we pin this point and then apply 170, it will push our frame inwards. Okay, so when we have an inwards push of the fiber or orientation of the fiber inwards, therefore it is negative. So negative 170 is to be added here so that this will become approximately equal to 0. So actually we have a slight difference because of the rounding of numbers. Anyway, so this will just go back to 0 here. And of course it will be connected by straight line. So this is a decreasing line here. So when we have a decreasing, we use concaving downwards as a connector. 170, 169, and 0 here. Okay, so here it is. Anyway, this is second degree curve because this is the first degree curve. Okay, so this is our moment diagram for member AB. Okay, so moving on to the other member here, we have this as our beam, and then we start with 170 couple here. And of course, 170, it's obviously pushing or orienting our member BC outwards. So when we have an outwards, that is denoted by a positive couple. That is positive 170 starting at joint B. So here it is. And connected by straight line, we deduct the area 5 here. So that is obviously 165. And then 165 less this negative area here will become 0. So our connectors, of course, is just a straight line for this member. Okay, so we have now the complete shear and moment diagram. Okay, so I hope you have learned how to determine the shear and moment diagram through this video. So it's up to you to improve yourself by having more problems or practice problems. So perhaps you can use a problem that is having a diagonal members as well as the distributed loads for your for sharpening of your skills in problem solving regarding the shear and moment diagram of your frame. So long and stand by for another video.